Okay, we want to go through all the fluid power problems in your book real quick. Fluid power deals with obviously fluids. There's two types of fluids. You can have liquid fluids or you could have gas fluids. So that's the difference between what we call hydraulics and what we call pneumatics, if you see right here. Hydraulics is the use of liquids like oils and things like that, flowing under pressure to transmit power from one location to another. Pneumatics, pneuma, means breath or air. The use of a gas flowing under pressure to transmit power from one location to another. So pneumatics is gas, hydraulics is liquid. There's a whole bunch of things here that talks about what's better about one than the other. I already sent a video on there that somebody else made that you can go through and kind of hear some things about some of those things. There's basic fluid components. These are schematics of different kind of things, reservoirs and lines and pumps and all kinds of stuff, flow control valves, directional control valves, check valves. You don't really need to know a ton about that, but there's some interesting schematics there for some of those things. Okay, so we'll get down to here. Properties of gases. So gases are affected by three variables: temperature, pressure, and volume. And so it's going to be important that we know we're going to do some equations here, some math equations, and there's some things you need to fix before you can do some of the math equations. So a couple things that we have here, we have pressure. Pressure is in pounds per square inch, PSI, and there's atmospheric pressure, and atmospheric pressure is basically how much pressure you're under at all times. There is a huge amount of weight of air molecules that is on top of you. So there's an actual quite a bit of pressure. You don't really notice it because you have an internal pressure in your body that balances out. But there is an atmospheric pressure, and standard atmospheric pressure is 14.7 PSI. You're going to want to remember that, 14.7 PSI, because you're going to have to always use that. There's gauge pressure, so this is atmospheric pressure. There's gauge pressure. Gauge pressure is basically what the gauge reads. If you blow up a tire or something, you might have a gauge that reads how much pressure is in there. That does not account for any atmospheric pressure that's on all sides of the system. Basically, it takes the atmospheric pressure out of it. It just says what's the exact pressure like in this tire, and it doesn't have anything to do with the atmospheric pressure. That's a problem because our math equations, when we're talking about different calculating pressures and things like that, we need to account for the atmospheric pressure. So what we're always going to use in our problems, this is very important to catch this, we're always going to be using absolute pressure. How do you find the absolute pressure? Basically, it means the overall pressure. It's very easy. You just take your you always add your atmospheric pressure onto the gauge pressure. So you have to watch the problem. If they tell you that it's an absolute pressure, you don't have to do anything. But if they say the gauge reads or the gauge pressure is something, you need to take that number and you need to add 14.7. We're just going to be in PSI only. We're not going to be in atmospheres or anything like that. So you just always need to add the atmospheric pressure. So the first question here is a gauge pressure. A gauge pressure reads 120 psi. What is the absolute? What is the absolute pressure? Obviously, that's pretty easy to do. You just add 120 plus 14.7, and you get 134.7 psi. Okay. Good. All right. So another thing that we need to talk about before we start learning how to do equations is something called absolute temperature. Absolute temperature. All these gas laws equations that we're going to learn, not only do they need to be an absolute pressure, which means you have to add the 14.7 to your gauge pressure, but they also have to be in certain temperatures. They have to be an absolute temperature. Absolute temperature, generally what we use is Kelvin, and the way to convert from Kelvin from like Celsius is to add 273. Kelvin equals Celsius plus 273. But and on all the problems that you see in this book, I remind you that temperature needs to be is Kelvin based. It says Kelvin based. I should clarify that. Basically it's absolute temperature based. So you can have it in Kelvin, or you can have it in another very kind of unused scale called Rankins. That R stands for Rankine. It's kind of Rankine. Rankine. And so if the temperature that's given in the problem is in Celsius, you're going to add 273 and use Kelvin temperatures. But if the temperature is given in Fahrenheit, okay, you don't need to convert to Celsius and then to Kelvin. Okay, so which is something I've done all the time. Technically, Rankine, you can use Rankine too. The ratios will work out. So if you're given a temperature in Fahrenheit, add 460 to it before you use the temperature in your problem. So 8.2 says that the temperature of the air in a system is 65 degrees Fahrenheit. What is the absolute temperature? You don't have to put the absolute temperature in Kelvin. The easiest way is just to take 65 and then add on 460 to give you 525 degrees Rankine. That is a completely acceptable absolute temperature, and you'll be able to use that in the problems we're going to do. Okay, so just to review, your pressures need to be absolute pressure. You need to add 14.7 to any gauges, and your temperature needs to be in either Rankine or Kelvin. So if your temperature is given in Celsius, add 273. If it's given in Fahrenheit, add 460 and use those temperatures instead. All right, let's get to some problems there. Okay, so the first one we're going to look at is called Pascal's Law. Pascal's Law is pressure. Pressure equals force over area. Now you might remember from the last unit that technically is also stress. Stress was force over a cross-sectional area. Okay, and force is in pounds, and the area usually is in cubic inches, right? Or square inches. So that's also abbreviated as PSI. Pressure is in PSI, but so was stress. So really, we've had this equation before, and you use it basically exactly the same way. 8.3 says, how much pressure is exerted in the following diagram? We have force on this piston, and the piston is a circle with a diameter of 3 inches. So the pressure is going to be the force, which is 50, over the area, cross-sectional area of a circle, which is pi, r squared. What's r? Well, the diameter was 3, which means the radius is going to be 1.5 inches. And don't forget to square it. A lot of people forget to square it, and that would be a problem. Okay, so if you do the math there, if you check the math on there, I think it should be like 7.1 psi for that problem. That's Pascal's Law. We're going to use it. This is pneumatics because we have air in the chamber. We're also going to use Pascal's Law with hydraulics when we have liquid in the chamber. Okay, so force over area, which is kind of your stress equation again. So that should be kind of review. Now we have ideal gas laws. We have 3 laws. We have Boyles Law, Charles' Law, and Gay-Lussac's Law. The reason we have 3 is because there's 3 different variables that describe these gases. Boyles' Law relates the pressure to the volumes. Charles' Law relates the volume to the temperatures. And then the last one, of course, would be Gay-Lussac's Law, which relates the pressure to the temperatures. So remember, in these, the pressures need to be absolutes. The temperatures here need to be either in Kelvin or Rankins. They need to be absolute temperatures. So remember that when we're doing all 3 of these problems. Okay, and you can use your notes on the test, so you'll have these equations to be able to do. All right, so let's look at Boyles' Law, which relates the pressure to the volume. And we have a question here, 8.3. 8.3, and it says a cylinder is filled with 40 cubic inches of air at gauge pressure of 60 psi. All right, so what do we got to do? We got to fix the 60, right? So we're going to add 14.7 to the 60, and this pressure so this volume, a cylinder filled with 40 cubic inches, that's That's when we're going to call that volume 1, right? The gauge pressure is 60 plus 14.7 should be 74.7. That would be pressure 1. Okay, so what happens? The cylinder is compressed down to 10 cubic inches. That would be volume 2. Okay, so that's volume 2. What is the resulting absolute pressure? So we're solving for P2. So P2, if you look at Boyles Law there, P2 should equal P1 times V1 divided by V2. Okay, so I can take, I can plug all those things in. P1 is 74.7, and I'm going to take that times V1, which was 40, and I'm going to divide that by V2, which was 10. Okay, 40 divided by 10 is 4, and you take 4 times the 74.7, and you should get, let's see, a pressure of basically 300. It's about 300 psi. You should check that work and see if you can do these problems. Okay? All right. Let's look at Charles' law. Charles' law relates the volume to the temperature. It's volume over the temperature this time. And remember, the temperatures need to be either in Rankins or in kelvins. So it says an expandable container is filled with 28 cubic inches of air. So that's volume 1. V1 is going to be 28 cubic inches. And it's sitting in ice water that is at 32 degrees Fahrenheit. 32 degrees Fahrenheit. Okay. So what we need to do with that is we're going to convert that to Rankins. So I'm going to do 32 plus 460, and I get a 492. So I'm going to do T1 is going to be 492 Rankine. The container is removed from the icy water and is heated to 200 Fahrenheit. So that would be a T2. I'm going to take 200 times plus 460, and I'm going to get 660 Rankine. And I'm trying to solve for the volume. Notice I say gas laws are Kelvin based. Well, they can also be Rankine based, so don't get confused by that. Okay, so I need to solve for V2, and the way I would do that, I'd take V1 times T2, and I'd divide by T1. I'd cross multiply and divide by this one here, okay, to get my V2. And if you plug all that in, I think I got a volume 2 of like 37.6 cubic inches. Okay. All right. That's that. Okay, we have one more law here. We have Gay-Lussac's law. Gay-Lussac's law relates the pressure to the temperature. It says a 300-inch cubed sealed air tank. That's the volume, but the volume's not in here anywhere, so that right there is really completely irrelevant. It's not part of the problem. In the morning, the temperature inside the tank is 62 Fahrenheit. So 62 plus 460. We're going to do T1 is 522 Rankine. The pressure gauge reads 120. So P1 is going to be 120 plus 14.7. That'd be 134.7 psi. Okay. What would be the absolute pressure? Oh yeah, what happens? So expected the temperature in the afternoon is expected to be 90 degrees Fahrenheit. So I take 90 plus 460, and I get a 550 T2. T2 should be 550, and I'm trying to figure out what's the absolute pressure, P2. So I'm going to multiply these two together and divide by this one. So P2 equals P1 times T2 divided by T1. And if I solve everything there, I think I get a pressure of like 142 psi for that one there. Okay. All right, hydraulic power. We had talk about the difference between hydraulic systems versus pneumatic systems, or liquid, or liquid versus gas systems, basically. Again, we have Pascal's Law, which is pressure is force over area, cross-sectional area, or stress, same thing. We've done this several times in the last unit and now this time, and so we're going to continue to use it. And so we have a hydraulic system here. You can lift an entire car with some system like this. You can have a small cylinder and apply a force on it, and you'd have to push it way down in, but this other cylinder, the bigger cylinder, would lift something really, really massive. It wouldn't lift it very far, but it would lift it. So we can use this as kind of a mechanical advantage. It's a lot like a kind of a simple machine. Okay, so if we look at this problem here, it says in the above diagram, what resistance force could be lift on the big cylinder? So I could have like a big car right here, or something that I could lift off the ground, and it's asking me what type of how big of a force could I lift with this if I applied 100 pounds of force on this 4-inch diameter cylinder. Okay, so pressure or stress was force over area, right? So this, I can equal this. This can be pressure in. Basically, I can do the pressure input would equal the pressure output, assuming it's an ideal machine. I can just have the pressure in be the pressure out. So what I'm going to have is I'm going to have force over area, force 1 over area 1, would equal force 2 over area 2. Okay, so that would be force 1 over, what is the area? The area is a circle, right? So it would be pi r squared, and that would equal force 2 over pi r squared. Now you'll notice, and when you're doing an equality like this, I'm dividing both sides by pi, so I don't really actually need it. Okay, so I can kind of get rid of that. Now I couldn't do that if I was actually trying to find the pressure like exerted on the first thing. I would actually have to do it, exactly like this shows. Okay, but if I'm doing this equality here, I can have pi on both sides. I can go ahead and cross them off. As a matter of fact, I don't even need to figure out the radius. I can use the diameters in here in place of the radius. The ratios will still be the same. Okay, so if it bothers you, then just find the radiuses, divide the diameters, this one and this one, by 2 to get the radiuses and plug it in. But you don't have to. So this problem would be 100 over. I could take the radius squared, which would be 2 squared technically, or I can just square the 4, which will work also, 16. But you just got to make sure you do it on the other side. And then the output force over its radius squared or its diameter squared, 144. Okay, so I take 100 times 144, divide by 16, and I get an output force. I could lift 900 pounds. 900 pounds I could lift with this hydraulic lift. Okay, there's another question here. What is the mechanical advantage? Well, the mechanical advantage, remember, is your force output over your force input, right? So I only used 100 pounds of force, and I lifted 900, right? So my mechanical advantage is 9 times, okay? 9 times. You can also divide the diameter squared, or the radius is squared, or the areas, right? If you divide the areas, either way, if you do like 144 divided by the 16, you get 9, right? So we're assuming this is an ideal mechanical advantage, right? So I do get 900 pounds of effort or resistance force out of it, just putting in 100 pounds of force. Okay. All right. Another thing we have is called flow rate. Flow rate. Q equals V times A. So what is this? Flow rate is how much volume is flowing per time. Okay. So like you'll see there's units, gallons per minute, or we have inches cubed per minute, either way. We have flow velocity, which is in inches per minute. It's like a meters per second, or a feet per second, or miles per hour, or something like that. And the area is the cross-sectional area, which of course we want to still be in kind of inches squared. So we kind of got to make sure that our units are somewhat correct here when we're doing these problems. Let's attempt this problem here. It says a flow meter attached to the main line in a hydraulic system measures the flow rate, which is Q, the flow rate, Q, at 15 gallons per minute. The line has an inside diameter of 2 inches. What is the flow velocity? How fast is the liquid flowing? The velocity. So we're solving for V here. So I can just do that real quick. V is going to be Q over A. But I need to make sure I have everything in the correct units. My area, this would be Q over area, and the area is a cross-sectional circle, right? So it's going to be pi r squared, okay? And the radius is going to be, the diameter is 2 inches, so the radius is going to be 1 inch. So the area down here is going to be inches squared, right? So, I'll go back this way. It's going to be Q over pi times 1 squared. So what does the Q need to be? Right now the Q is in gallons per minute. Gallons per minute. I want that to be in inches cubed per minute. So they gave me a conversion factor here. So I'm going to do 15 gallons per minute. And I can do 1 gallon is equal to 231 inches cubed. Gallons will cancel, and I'll be in inches cubed per minute. So I take 15 times 231 to get my flow rate, my Q. Okay, I'll do that real quick. 15 times 231. I get 3,465 over pi r squared, and 1 squared is 1, so it'd actually be over pi. Okay, and if I do that, I get like 1103. This would be inches cubed per. No, it wouldn't be just inches per minute. Inches per minute, because I was solving for the velocity. Okay, all right. So if you think about it, this inches cubed per minute, that's kind of a volume per minute, and you're dividing by area. So you're taking inches cubed divided by inches squared, which gives you an inches per minute. So that works out pretty good and pretty obvious. Okay, there's one more thing here, and it was in some of your other videos in your notes, called Bernoulli's Principle. An increase in velocity results in a decrease in pressure. Likewise, a decrease in velocity results in an increase in pressure. Okay, so here we have what's called a Venturi tube, represented by a decrease in the diameter of it. At the narrowed point right here, the speed increases. It gets a little faster, and therefore the pressure decreases there. This is important in hydraulic systems because the size of a conduit or piping in a system will likely vary and impact the system based on this principle. Okay, and there's some other things you could read about there. All right, I think that's good enough. Hopefully those are the equations you're going to use in the E-Lab and then on the JEDI trial. So see how quickly you can get all that done.